All right, so I'm Andrey. I'm a regular C++ programmer, and I love templates. So I'm going to talk to you about making template instantiations more readable. So what's the problem, right? So we have these template classes which have, many parameters. Some of them are default, and when you want to like configure some of this, you so run into the problem where you may need to specify all of them. They usually work well, for example, in this hash table. They work well when you specify just a few of them like this, right? It's like it's your normal map or another map, you just key and value. But if you want to say customize this small buffer um, optimization size, you kind of have to go through all of them and end up with something like this, right? So this is kind of not readable in my opinion, and you don't know what the 32 is unless you look at the definition. And you also have to specify all of these parameters. And also, if you have like an allocator, this becomes really hairy. Um, I've been working for GFT companies, and we usually create all of our code as a templates, and we have different like senders, receivers, algorithms, and we usually end up with a bunch of uh, code that gets assembled together in a final form from multiple templates and template parameters. So what we do there is we just say, well, we'll just have a config class. This is like a policy uh, based design where your config defines all of those parameters. And what you can also do is you can define like a default config. You can see here for our hash table, we have the same sort of values here, which are coded to the default and SBO size, etc. And then you can use this default and your hash table to query what you've been given, right? Because in this case, your parameter is just a new struct which defines some of these parameters for your template. We use a bit of C++20 concepts to figure out what you have specified, so we can choose a default. So we instantiate a default here, and then we use conditional T to say either use me the say hash from the default or from the provided config class. So with all of these combined, the instantiation would look like this, right? So we have this class that defines our customizations like key value and SBO size. And then we instantiate our hash table with our custom type. This kind of works well, and it's very flexible. You can do a lot with this uh, configs. You can do use inheritance. You can put more stuff in there. You can put like functions and context pairs, constants besides the types, templates, and some nested structs. But what I find difficult with this is that it's not easy to figure out what goes in there because it's not stated anywhere. And the other problem is that the config is usually defined somewhere else. So it's not, you have to jump back and forth to read what has been defined because it's not obvious at the instantiation spot. And also for every instantiation, you kind of have to create a new config if you want to customize something, not really convenient. So the other approach you can do is sort of define these tag types. So here we have a key type, which just takes a parameter as a key and just wraps it around. So we'll use the struct name as the name of the parameter. So we'll have all of these. You can define them for the values and for templates, just small tags. And then you will pass them as a list as a variadic list of parameters. And query them by tagging your implementation, just saying like get param and then use the tag like get key, get value out of those specified parameters. So the magic behind this is pretty straightforward in a sense, but it is reusable. So there's a very neat trick in here. We're using the variadic inheritance either from an empty class or from an instance of this tag type. So we end up with the right type or with a compiler error. So when we put all of this together, the instantiation looks like this. So we clearly state that what the key is, what the value is, and the SVO size customization. So it's pretty, I think it's pretty readable. And also all of the parameters are at the instantiation. You can mix and match them, you can skip them, you can use the defaults in the same way as we used with the config parameters. But one issue with that is that all those tag types, they kind of become global, and you need to come up with sort of unique names, although I think they can be reused. But I think overall, this is a pretty good approach that lets you do pretty readable instantiations. So the other technique I'm thinking about here is that for regular functions, we have kind of solved this with designated initializers. If we need like a list of parameters that have like the same type and we want to give them in, we'll just use a struct and then call the struct using the designated initializers with the name like this. So this is, I think, quite readable and unambiguous, and you can also define defaults and skip the default initialized parameters. So pretty handy technique. And so I've been wondering if we could use something similar for templates. And for non-template parameters, we absolutely can. So here I've wrapped the SBO size, and then I'm passing that as a part of the config. And then you just access the members in your normal fashion in here. So for this parameter, this is only one because we had only one non-type parameter. It looks like this, right? So we can use the same syntax. We can just say $SBO size is 32. So it's already a slight improvement compared to what it was originally, which is just 32. But like we want to pass the types as well. So how do we do it? Well, because it's going to be part of the config and it's still a type, we want to use the same type for all of the instantiations because we don't want to define a new type every time. They kind of need to be in the template as well. And then the question becomes, so how do we pass it into our hash table? So what if we can put an auto config in here, and that kind of works. But the problem is that, again, is discoverability. We don't know like which parameters we need to pass here, what works here. Well, it turns out that CTAD works for non-type template parameters, so we can just do this. So, and then when you instantiate this template, then the compiler will be able to deduce the template arguments from your config types. And that works for all types. For example, you can do this with the standard array. You can just say this without the type and the number of arguments. And then when you call it with just a list of numbers, the actual type and the size gets deduced. So this works for all of your context for structs and classes. So with all of that in place, our instantiation looks like this. So we still have to pass the type names explicitly, and this is not ideal because like we don't know which, if especially we specify more than one, we don't know which one is means what. So what would ideally this look like? So ideally we want something like this, like we do for the regular function arguments, right? We want to just say like key equals int and value equals string. Well, what if we turn types into values? We already have a facility for that, which is called type identity. So we'll just define a variable that takes a type and then pass this value to our config. So we'll define the parameters like this, and then define this struct with this type variable, specifying it like this. So we can pass this, but we still need to specify the types for the config explicitly. Well, it turns out that ctad works here as well. So you can use ctad to deduce your parameters from the initializer list. So this becomes just this. So we don't need to specify the types for the template because it gets deduced. We just specify the parameters using this variable. So once we put everything together, our config would look like this. So we have a number of type identity values here, some of them default initialized, and the defaults are specified in the template head. We can pass template parameters as well in this manner. So I've devised a small variable called template, just wraps around, but it's pretty similar to what type identity is doing. And then when we go and actually use it, we pass the config as is without template parameters because it gets deduced. And then for the type parameters, we just use decal type of the field, which will be the type identity in this case, and we use colon type to get the actual type.
Andrey, sorry to interrupt, but we're over time here. Can you just get up your final slide?
Yep, so the final slide is, this is how the instantiation look like. And for templates, and you can pass a lambda, and this is the compiler support. It works on the latest releases of everything in GCC. And in Clang, you need 18 or use this syntax. That's it.
Awesome. Thank you.